here, and we have been covering the chapter on the isotopic separation and enrichment, and that includes covering the nuclear fuel cycles, and that's an important topic, of course. We'd like to cover today all the methods that we know of that are used for enriching the fuel. It's an industry by itself, the industry of isotopic tailoring, because in applications, we know that the different isotopes have different properties that can be used to our advantage. We looked at different nuclear fuel cycles last time. Today we expand the topic in looking at the different enrichment methods, and also study the nuclear fuel cycle. So answer a question on how much, for instance, a utility executive, some of you will become utility executives, how much does he have to order in terms of the fuel that is needed for his nuclear reactor. Last time we stopped at looking at the three different nuclear fuel cycles. We did not cover the thorium fuel cycle here, but the existing cycle in the United States is what's called the once-through fuel cycle. You mine the uranium from the ground, you take it to a nuclear reactor, you enrich it over the natural enrichment of 0.72% to 3 to 5%. You burn as much of that uranium-235 and some of the produced plutonium in the uranium-238 cycle in a nuclear power plant, and then you store the fuel for some 10 years maybe, and then in the same way that you mine the uranium from the ground, you dispose of it in the ground. However, it still contains some useful uranium-235 fuel. It contains also some useful plutonium fuel. So you find that Europeans, Japanese, Russians, reuse that plutonium. They recycle the fuel, get the uranium out, the 235 out that hasn't been burned, the plutonium, and reproduce the cycle back again. This is called the mixed oxide or the mixed oxide fuel, uranium dioxide plus plutonium dioxide. For the long term, we have to think about breeding. So in that case, that's a different nuclear fuel cycle where you use the depleted uranium-238 to produce plutonium. And this is where the vision of nuclear energy really is, in the sense that you can produce, in fact, more fuel than what you consume. So you get an infinite energy supply. In terms of the plutonium, if you don't burn it, what happens to it? Well, if plutonium is produced in the uranium-238 fuel cycle and you do not burn it, it would be wasted. Well, not quite wasted, because in nature, it emits an alpha particle and then it turns into uranium-235. So you have here a set of 4 chain reactions. A neutron is absorbed in uranium-238, produces uranium-239. Uranium-239 emits a negative electron, an antineutrino, and a gamma photon, becomes neptunium-239. 239 is radioactive, so it emits also a negative electron, an antineutrino, and a gamma photon, and becomes plutonium-239. Plutonium-239 itself emits an alpha particle and a gamma photon and becomes uranium-235. So if you cancel out on both sides of the equations what we would call catalysts in chemistry, you end up that a neutron added to uranium-238, which is the fissionable but not fissile isotope, eventually gives us 2 negative electrons, 2 antineutrinos, 4 gamma photons, and then turns back into uranium-235. So nature some kinds of recycles itself. So we have the once-through fuel cycle in operation today in the United States. The justification is that uranium-235 is cheap. So it's a matter of, it's a wasteful cycle. Again, the different other countries that have facilities for recycling the fuel or reprocessing the nuclear fuel are using already the thermal reactor recycle. And in the future, we will have to develop the fast reactor breeder system if we do not go to the thorium cycle, and if we do not also adopt the route of fusion energy. All right, we want to become a little quantitative here and ask a question. How much fuel does a nuclear power plant has to order from a mine to keep its operations going? Notice that it's a long-term kind of contract, because you want to operate your nuclear power plants not just for a year, but your capital investment means that you really at least operate it for the licensing period of 20 years. So let us take a reactor that produces a certain amount of thermal megawatts of power, and we'll designate that as P sub TH for P thermal. And let us say that the recoverable energy per fission event is 190 million electron volt per fission. In the textbooks, I take it as 200 million electron volt per fission. What they're doing there is that they're including the anti-neutrinos, but we know that the anti-neutrinos energy is not recoverable. They can go all the way through the thickness of the Earth and reappear from the other side without changing or interaction whatsoever. So we're going to take the value that is more realistic of, or actually an actual value of 190 million electron volt per fission event. We can write an expression for the fission rate, d fission by dt, proportional to the thermal power that we get from our nuclear reactor. So that should be equal to the thermal power in megawatt thermal, but we want to turn it into how many grams per day, or how many kilograms or metric tons. 1 metric ton is 1,000 kilograms per day. How much really a mass or a weight are the amount of fuel that we have to purchase for that power plant. So we are going to use a process of dimensional analysis. We turn our watt into the megawatt into watts. So we have 1 million watt per megawatt. Mega means 1 million. And each watt is 1 joule per second. Watt is a unit of power. Joule per second is energy per unit time. That is power. Now, that joule per second, if we divide into 190 million electron volt per fission event, should give us how many fissions occur per day, or the fission rate. Now, this is in million electron volts, so we turn that million electron volt into joules. So that is, we have 1.6 10 to the minus 13 joule per million electron volt. So million electron volt and million electron volt cancel out. And then we, this is per, this is per second. So we make it per day by multiplying it by 365 days in a year, 24 hours per day, 60 minutes per hour. And then you turn it into just from seconds into day. We have 86,400 seconds per day. And in that case, you find that all the units cancel except fissions per day. So the fission rate in a 1 megawatt, if you substitute 1 here, 1 megawatt thermal reactor is a tremendous amount of fissions per day, 10 to the 21st multiplied by the power of the reactor. It could be like 3,000 megawatt thermal. Now this is fissions per day. It doesn't tell us anything about the weight, how many grams or how many kilograms we are burning per day, because we are going to pay the mine in the value that we pay to the mine is really per kilogram of material or metric ton of material that we buy. So we invoke here again Avogadro's law. Avogadro's law says that 1 gram molecular weight, which is the mass of the material divided into its molecular weight, contains really Avogadro's number. Avogadro's number is written right there. So Avogadro's number is known. It's a constant of nature. We are going to take an approximation. Remember, we are burning the isotope 235, uranium 235. So we are going to approximate its masses in the denominator as uranium-235. And in that case, we can turn the number of fissions per day into some kind of a grams per day. And in that case, we call this the burn-up ratio, and we'll abbreviate it as BR, which is the fission rate multiplied into G divided into capital N, and that would give me, again, N here is the Avogadro's number, and G over N is basically the mass of the isotope capital M divided into Avogadro's number. So we have taken here Avogadro's number, G divided into N is M divided into Avogadro's number using the scissors rule. And by getting the fissions per day and then multiplying by the weight of uranium-235 M per fissions and fissions cancel. And lo and behold, we end up with grams of uranium-235 per day. And it's a very simple number to remember. It tells me that the burn-up ratio of uranium-235, how many grams of uranium-235 we burn per day, is 1.1 the power of the reactor in megawatt thermal. Or if you say, I have 1 megawatt thermal, I am going to burn only 1.1 grams of uranium-235 per day. Compare this to a coal power plant that would need a whole train of 100 cars per day of coal to produce the same amount of power. And that's an indication on how nuclear energy has a very high energy density or energy per unit volume, or also we can say it had a very high specific energy or energy per unit mass. We only need 1.1 grams of uranium-235. All right, so we want to refine that number a little bit because some nuclei of uranium-235 can absorb a neutron and not fission. They would turn into uranium-236. So in fact, we need more than 1.1 gram of uranium-235 per day to account for that U-236 that is formed. And it's an even numbered isotope, so it won't fission. It's maybe fissionable as we use the taxonomy or the terminology. So we need a little more than that amount of uranium-235 to account for radiative captures that are not useful, that are not going to produce power for us. To be able to take that into account, we take the ratio of the probability that a neutron is absorbed and produces a gamma photon, turning the uranium-235 into uranium-236, divided by the probability of fission. So we need a little more uranium-235 to account for that formation of 236, and that is not going to fission. The ratio B here is the ratio of what we are going to call later the microscopic radiative capture cross-section to the microscopic fission cross-section. And it's a measurable quantity for uranium-235. And then when you take the number of fissions plus the number of radiative captures relative to the number of fissions, it becomes 1 plus B, or sigma sub F plus sigma sub gamma divided into sigma sub F. We call that sigma sub F plus sigma sub gamma the absorption cross-section. The neutron there is absorbed relative to the number of fissions. So we really need to multiply that burn-up ratio by that number to account for the formation of 236 out of uranium-235. And so in that case, when we multiply by that ratio of 1 plus B, we change the terminology. We don't call it the burn-up rate anymore. We call it the consumption rate. We are consuming that uranium-235, both for fission and to allow for the radiative capture or neutron being absorbed, turning it into uranium-236. If you use uranium-235, that 1 plus B ratio can be calculated really as the B here is 0.169, meaning that we have 0.169 atom of uranium-236 formed per atom of uranium-235 fission. So that number that is what you said, gave earlier is 1.1 gram burned up of uranium-235 per day becomes a little bit more, 1.2 grams of uranium-235 consumed per day, and we call it the consumption rate. Let's say 1.3 grams per day. Still a very small number per megawatt thermal. For instance, if you have a 3,000 megawatt thermal plant, you multiply this 3,000 per 1.3 and grams per day, divide into 1,000 gives you kilogram, divide into another 1,000 gives you metric ton, because 1 metric ton, T-O-N-N-E, in the SI system of units is not the same as 1 ton, T-O-N. And please notice that in your engineering profession, TON is a British system of units or the American system of units, but not the SI or the metric system of units. So 1.3 grams per megawatt thermal of power produced in general. The consumption rate, as we have written it, is 1.12 grams per day. If you want to contract with a mine to provide you with a certain amount per year, you multiply that amount per day by 365 days per year, and you get how many grams of uranium-235 you get. You need per 1 megawatt thermal of power of your reactor per year. Now, this is, remember here, this is what we are burning is really the isotope uranium-235. But if you are going to order uranium from the mine, you are going to order natural uranium, which is 0.72% only uranium-235 as an enrichment. So if you want to calculate how much natural uranium now, not uranium just 235 per year, you divide that consumption rate by the enrichment. Let's call it X sub F, F standing for the feed in uranium-235. And in that case, you find that you have to, of course, order not just a few grams of uranium-235, but you have to order grams of natural uranium containing the uranium-235. Now, what do you do with that natural uranium? You send it to an enrichment plant. Enrichment plant job is to allow you to use water as a coolant in your reactor. Hence, you need to increase the efficiency, the enrichment of uranium-235 from the 0.72% natural uranium to 3 to 5% enriched uranium, so that you can account for the absorptions in the water in your coolant. In that case, you take this now that natural uranium with an enrichment X sub F 0.72%, you send it to an enrichment plant using one of the methods of enrichment that we are going to cover today. And you give them a certain amount, let's call it M sub F, a mass of the feed in kilograms or metric tons with an enrichment of the natural uranium X sub F. And then you end up with a product that has now an enrichment of 3 to 5% that you need for a light water reactor. And the product would be the mass of the amount that has that higher enrichment. And that's what you put into your reactor and start burning it. If you are going to increase the proportion of uranium-235 in the material that you feed into the enrichment process or enrichment plant, you'll end up with some uranium now, the tailings as they are called, that has a lower enrichment in uranium-235. Usually it's 0.25%. We don't go and we cannot extract really all the uranium-235 from the natural uranium because it will need a very large number of steps, and the economics simply suggest that you stop at a certain point. And now the question is, to get a certain amount of a product, how much do we have to buy a feed from the mine or the miner for the fuel? And that's very important, not just as a contract between the mine and the power plant. It's not just on a yearly basis, it's over a whole 20-year period. So that provides basically also stable economics and stable employment for the people, both at the mine, the enrichment plant, and the power plant. To figure out this, we need to carry out what's called the mass balance of the plant, the enrichment plant. We are feeding into it M sub F kilograms or metric tons of natural uranium. We are getting now M sub P output in the enriched fuel and M sub T in the tailing. It's very obvious that what we feed into the plant here, M sub F, should be equal to the mass of the product plus the mass of the tailings. If you want to be really sophisticated, then you have some losses there inside the enrichment process. Some materials get deposited on the tubing and so on, but this is minor, and we are going to ignore that part. And in addition, the amount of uranium-235 that comes into the plant, that would be the product of F sub F multiplied into M sub F, should be equal to the uranium-235 in the product, and plus the material of uranium-235 still left in the tailings. And this is a mass balance that we carry out in all engineering processes, whether you're doing heat transfer or hydraulics or neutron transport. You carry out a mass balance to figure out how much of a product you need and how much is a feed that you need to provide to the enrichment plant. Now, the interesting thing is that this is the two balance equations here allow us to have two equations in two unknowns. And you know in algebra that if you have two equations in two unknowns, then you can get really just solve the two equations. Notice that the product material that we get would be the consumption rate divided into the enrichment of the product, and that would be of grams of enriched uranium per year. Okay, let's write the two mass balances. There is one mass balance for what comes from one side of the enrichment plant, M sub F, and what comes as a product plus the tailing. So this is our first equation. We write here the first balance equation as M sub F is mass of the feed should be equal to the mass of the product plus the mass of the tailings. Wonderful. In addition, the uranium that's 235 that is being fed into the plant, which is the product of the enrichment of the feed multiplied into the feed, should be equal to the uranium-235 in the product plus the uranium-235 in the tailing. So that's the enrichment in uranium-235 multiplied into the amount of mass in the tailing. So X sub F, X sub feed, enrichment of the feed multiplied by the mass of the feed, should be equal to the enrichment in the product multiplied into the mass of the product plus the mass of the tailings multiplied into the enrichment of the tailings. As we said, we have two equations in two unknowns. We can eliminate them to figure out how much is the mass of the of the product and how much is the mass of the feed. Let's eliminate the mass of the tailings. It's not that important to us. So we use what's called the elimination process to solve the two algebraic equations. In the first equation, we express M sub T as the mass of the feed minus the mass of the product. And then we take this and substitute into the second equation. This is called an elimination process. We are eliminating M sub T so that we can figure out M sub F and M sub P. So let's eliminate the mass of the tailing in the second equation. And the tailing in that case is M sub F minus M sub P. Now we have an equation that has M sub T and M sub P as the variable. So in that case, let's multiply the tailings enrichment by the mass of the feed minus the mass of the tailing by the mass of the product. And then let's separate now the variables. Let's take on one side the mass of the feed here, bring this term to the other side, and you find that the mass of the feed is multiplied by the difference between the enrichment in the feed and the enrichment in the tailings. What the tailings are what's left out of the process, so you take it and store it for a future maybe breeding cycle in which you breed your plutonium-239 from uranium-238. And on the other side, when you separate the variables, you have the mass of the product, and that one is multiplied by the difference between the enrichment of the product and the enrichment of the tailings. And what are we interested in? We are interested in ordering uranium from the mine or the company that mines uranium. So we are interested in the mass of the feed. And depending on the mass of the product, I need a certain amount of product to keep of uranium-235 based on the equation that we wrote earlier, the mass of the product here, considering the power of the reactor. Here is the mass of the product, considering the power of my reactor, the consumption rate, in fact, divided into the enrichment of the product. So I need a reactor that runs on, say, 3% enrichment, and I need the reactor is 3,000 megawatt thermal. I can simply calculate what is the mass of the product that I need at the given enrichment of the product, say 0.03. Remember, when you say 3%, it's 0.03 or 3 divided into 100. So if I know the mass of the product and I know the enrichment in my product, and I know what is the enrichment in the feed, is obviously the 0.72%. Remember, that's 0.72 divided into 100. Then I can calculate the mass of the feed that I have to order from the nuclear power plant. What's usually done is that X sub T, the enrichment in the tailing, is down to from 0.72% of uranium-235 in natural uranium to 0.72% left in the tailing. So in that case, we can calculate the mass of the feed. I'll give you a problem today for a given reactor, so you would know its thermal power. If you know its thermal power, that's P sub thermal here. You can calculate the consumption rate. You can also calculate the burn-up rate. You know that you want to enrich, say, to 5% enrichment. You can calculate the mass of the products in gram of enriched uranium per year. Wonderful. Now you substitute this one in that equation here, the mass of the product, and you have again the 5%, say, enrichment that you want. You know that the tailings is 0.25%. And in that case, you have, the enrichment in the feed, which is 0.72%. You can calculate what is the mass of the feed, which is the amount that you have to order from the miner. And that could be an amount per year, or you can turn this into amount over a 20-year period. So it keeps you in business as the utility executive, and it keeps the miners also in business over a 20-year period. Why? The licensing period for nuclear power plants is 20 years. After 20 years, you need to renew the license after a safety inspection. And nuclear power plants have basically most of them increased their licensing period from the 20 year to 40 years. Some plants are trying to extend it to 60 years, and some even are talking about 80 years, almost a lifetime, producing power for humanity in general. All right, now we talked about that enrichment plant. So what goes on inside that enrichment plant? We have 6 processes or 7 processes that can be used for enriching the uranium or increasing the proportion of uranium-235 in the feed of natural uranium. So from 0.72% to 3% to 5%. If you are building a research reactor, you go to the 20% enrichment, or a fast reactor, you also need to go to the 15% enrichment. If you are going to run a nuclear submarine for the Navy, you can go up to the 95% enrichment. And if you are building nuclear weapons, you go also to that 95 or 98%. We are interested, of course, in the situation, the 3 to 5% that we need for light water reactors, because this is the dominant system that we have today. If you remember the German program, the Germans had some kind of experimentation on the enrichment, just an experiment in the lab. They really never developed the process of enrichment to any commercial degree. Same for Japan. The United States pursued that process much, much more. and to a success, in fact. But when the processes of enrichment were first being explored, there was not any knowledge about what are their industrial characteristics. So many processes were tried and simply abandoned because they didn't have any promise. Some processes were pursued, as we'll see, and then afterwards they have been replaced by more energy efficient processes. The first process that was used is the process of thermal diffusion. If you have a molecule of any material, you'll find that the lighter molecule can propagate in a gas at a faster speed than the heavier molecule. So that was used to an advantage in using tubing, as you could see here, heated by steam. And on those long tubes here, you feed any kind of chemical that contains uranium, like you can think about uranium hexafluoride or uranium tetra or uranium. This is uranium hexafluoride. You find that the lighter molecules would be more concentrated near the hot surface than the heavier molecules of uranium-238 hexafluoride. Now, why hexafluoride? Because fluorine in nature has only one single isotope, fluorine-19. However, uranium has different isotopes. So in that case, you can differentiate between the molecules of uranium hexafluoride 235, uranium-234 hexafluoride, and the ones for uranium-238 hexafluoride. So there is a separation that happens in that case, depending on the temperature of the heated surfaces. Steam was used. The plant leaked lots of steam. The United States Navy, I think, carried that process. They built a plant just for that purpose. It needed to be cooled by water, so they used the Clinch River near Oak Ridge in Tennessee. Tennessee has lots of water supplies and coal supplies, so that was built there. And I think we have a picture of that plant here. You notice that's a huge industrial process. It's not something that a non-national group can carry out in their basement like some people pretend that non-national group can do it. It needs really the whole industrial might of an industrial nation, not any third world nation without any industrial capability. So that was the S50 thermal diffusion plant at Oak Ridge, Tennessee. And basically the process was not very successful. The steam kept leaking all over the place. So it may have reached some enrichment just for experimental purposes, but nevertheless, it's a thermal process. Another process that was relatively successful is to use the electromagnetic separation process. So you use electromagnetic field, in that case, a magnetic field, in fact. And in the electromagnetic separation, you use the process that was invented in the cyclotron. The cyclotron is a particle accelerator that accelerates the particles like protons and or ions in general in a magnetic field. And that's why it has been called the Kalitron. The electromagnetic separation has the other name Kalitron, standing for California cyclotron. California cyclotron. Now, what do you do there? You start with accelerating through a potential voltage, capital V, some molecule of maybe uranium-235 and uranium-238. In fact, what they use is uranium chloride, but to simplify the equations, I'm simply using the mass of uranium-235 and the mass of uranium-238. So if you take the charge on the molecule of the 235 as Q, when you multiply the charge by the voltage, you accelerate the particles to a kinetic energy of half mv squared. Notice that 235 compared to 238 is a lighter isotope. So this one has now a kinetic energy half m235 v squared. and the heavier isotope 238 is half M238 V squared. I'm ignoring the 234 here because it will join with the 235. From that equation, you notice that you can calculate the speed of those ions, in that case of 235, in terms of the voltage that you apply, but it's not, notice that it is proportional to the square root of the inverse of the mass. So if you take the one for the 238, if they both have the same voltage, the larger mass of 238 would mean that it would have a lower velocity. Now, when particles are subjected to a magnetic field, there is a law of nature that says that they are, in that case, subject to two forces. Now, we are talking about an electromagnetic field. This means that it's a combination of an electric field and a magnetic field. If the electric field is E and as a vector because it's directional, you'll find that the force on the charged particles is equal to the charge of the particle multiplied into the electric field, and the force as a vector and the electric field are in the same direction. This means that if you accelerate an electron between the plates of a condenser, you'll find that the electron is going to move from one side of the condenser to the other. However, if you have a magnetic field, the situation is very different. The force that comes out is the cross product of the velocity vector of the particle into the magnetic field vector. This means that it is perpendicular to both the velocity vector, the direction that the particle is moving in, into the magnetic field. And that means that if you have a magnetic field that goes in the direction, say, of my arrow like this, the charged particle moves around the magnetic field. And in fact, that V cross B force multiplied into Q, the charge, would be equal to the centrifugal force, V squared over the radius R, and the particle would rotate around the magnetic field lines. All right, let's assume that we don't have an electric field, that we are using only a magnetic field. Then the force on the particle will rotate the particle around the magnetic field line. And that force here is going to be canceled by the centrifugal force, which is mv squared over the radius r. We are taking the magnitude now. So V multiplied into B, the magnetic field strength. Q is the charge of the particle. V is the speed of the particle. That is the force F. That force in the magnetic field rotated with a rotational speed, or the mv squared over r. Notice immediately here that you have a different radii for different masses of particles if the magnetic field strength and the V and the Q are a constant. So you find that to be able to equate FVB into mv squared over r, the mass over r should be a constant. So a large radius implies a small mass, and a large mass implies a large particle. All right, so let us quantify this. Let's take the two isotopes, so uranium-235 isotope and uranium-238 isotope, and plug in that equation. Each one of them would have a different radius. So the lighter isotope would have a radius R235, and the heavier isotope would have a radius 238. So in fact, you can calculate the radius here for each isotope. R235 is equal to M235 multiplied into the speed of the particle divided into the magnetic field strength and the charge of the particle. This means that in our equation here, the radius for 235 is going to be the square root of twice QV M235 divided into the magnetic field multiplied into the charge. And if we solve for the radius for 238, you find that we get a different radius that is dependent on the mass of the 235. Now, this equation is simplified because, in fact, what they used was a molecule of uranium chloride. So we would have complicated the whole system by taking basically the chlorine into consideration. The important thing is that the two isotopes injected into a magnetic field as ions would have different radii, because everything is a constant here except for the mass of the isotope. So we can separate the isotopes into two different radii depending on the mass of the isotopes. In fact, if you have that Lorentz equation, or what the French call the Joule's equation, you'll find that the electrons would move with very, very, very small radii because their mass is small compared, say, to the ions. So in the Earth's magnetic field, where in fact that process happens from the solar wind, now it's protons and electrons, you'll find that the aurora borealis is formed by the particles from the solar wind rotating around the Earth's magnetic field from the North Pole to the South Pole and back and forth and back and forth. And that's what we see as the aurora borealis in the north and the aurora australis in the southern hemisphere. So there is a difference in the radii. In fact, you can take R235 minus R238, and definitely there is a difference that depends on the difference, the square root of the difference of the uranium-238 isotope and uranium-235 isotope. And we can talk about the ratio of the radii. Definitely, there is a process in which the radius of 235 relative to the radius taken by the 238 nucleus in that case, or ion, is the square root of the two masses. We call this a separation factor, and you have to do this into basically, so you get a separation between the two. The experimental device would look like this. So what you do is that you create a vacuum so that the ions of uranium chloride, in that case, do not interact with the oxygen, nitrogen in the air. So you have here a vacuum pump that uses oil. You simply pump the oil out and suck the air out of the enclosure. So that creates a vacuum. So this is the diffusion pump or a vacuum pump. Then you do this in a chamber that is maybe steel, and you bring in coil here, a large coil of a magnet in that case. You can use, say, copper in the coil, and when you circulate a current in the direction of the arrow here, or the left-hand rule, you create a perpendicular field that is the field perpendicular to the page. Then you come in and accelerate your ions by evaporating them by an ion source, just heating them up. You'll find that in the magnetic field now, perpendicular to the page, the charged particles of the uranium, the lighter particle will take that radius here. This is a lighter isotope, takes a small radius, and the heavier isotope, uranium-238, takes a larger radius. All you have to do is place some kind of a collector here and a collector here, and you have separated uranium-235 from uranium-238. It's a separation ratio is proportional to that square root of the masses of the two isotopes. So here magnetic fields are used. We call that the electromagnetic separation process, or you can call it the Kalitron for California cyclotron. If you go to the first chapter, you could see pictures on how these magnets were constructed. Initially, they used copper during the Second World War, but then they ran out of copper, so they went to the strategic stockpile of the United States, where the gold and the silver, and borrowed most of the silver they had there. Silver is a better conductor, in fact, than copper, so they used the silver to create the bus bars for the electricity and the coils for the magnetic separation, electromagnetic separation process. Those chambers now are positioned in between two large magnets. You'll find here the two magnets, and this is a chamber in between them. This cross means here that you have wiring going all the way around an iron core magnet. So you have a magnet here, and a chamber in between them. You have two slits, and everything is calculated so that the magnetic field the magnets are taking that curvature here so that the magnetic field at the center is uniform. You inject the particles from one side and you collect them from the other side. So that is really the configuration of the California cyclotron or the Kalitrons. And the separation was successful with those devices. Just as a reminder, I'm going to backtrack to our chapter 1 in the semester and show you pictures of those Kalitrons. So let's go back to the first man-made reactor and birth of the nuclear age here. And if you go down, 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 we will be able to look at some actual pictures of those Kalitrons. The Kalitrons were used, in fact, to separate uranium-235 from uranium-238. But they were not very successful. They only produced gram quantities of uranium-235, which were very useful in experimentation, but they were not producing enough uranium-235 to make a nuclear device. And that was the Site X at Oak Ridge, Tennessee. They built 2 of those Kalitrons, one shown here. They call it the Alpha 1 racetrack, and the other one, the Beta track. It has a different shape, but on top of them, you could see here, that's a bus bar that's spreading the radioactivity, the electricity to those magnets. Each one of those is a magnet chamber, as you could see here. This is in the Alpha 1 track and the Beta track here. As I said, these bus bars were made, and the magnets were made out of silver. Wow. These were very large in size, in fact, because at the center here, in between the magnets, there were some young ladies sitting there. They call them the nuclear ladies, atomic ladies. They were controlling the strength of the current in a rheostat. This is a gentleman working on the coil for those magnets. Look how huge they are. This is one coil being inspected by an engineer here. Then they're put into the big shape of the coils and the current controlled by a rheostat by our young ladies there. The Kalitron girls, they were called. They gave them a nice name. And 14,000 tons of silver bars were borrowed from Fort Knox for that, and then returned after the war. The process, as I said, produced gram quantities, but General Leslie Grove, in his memoirs, he wrote the memoirs of his activities during the Second World War. He kept the process going, even though he named it as a white elephant. He knew that the Russians were spying on the United States, and he kept the process going to mislead them. In fact, he did mislead them. He sent them in the wrong direction. Okay, send them in the wrong direction. This means that the process was recognized as not very successful. The process that was successful, as I'll show you now, was the next process. So let's go back here. The next process was the process of gaseous diffusion. So we covered now 2 processes of enrichment. Thermal diffusion was not successful. The Kalitron or electromagnetic separation was relatively successful, but not 100% successful, because you need, as we learn later, kilograms quantities, thousands of grams quantities of the uranium-235 to make a nuclear device in the Manhattan Project. Gaseous diffusion was adopted, and it's still operational in some countries, like in France. And we try to separate now the 3 isotopes of the uranium-234, uranium-235, uranium-236. We use gaseous diffusion. So the terminology of gaseous diffusion definitely is the use of uranium hexafluoride. Uranium hexafluoride, shown earlier in the chapter, is a gas that's at room temperature is a crystal. you heat it before you insert it into the diffusion plant. Now, once it's in the diffusion plant, you use the property that the different molecules of those gases have different sizes. So if you have a molecule of one side or the other, the large molecules would have a lower mobility than the small molecule, or the 235 molecule would be here, uranium hexafluoride 235, and the larger molecule uranium 238 hexafluoride. So what you do is simply let them diffuse as uranium hexafluoride through a barrier. It's still a secret what is the composition of the barrier, but the fluorides are very, very corrosive. So I would assume it was a nickel type of sintered nickel powder barrier. You'll find that the mobility of the uranium 235 is higher than the mobility of the heavier 238. So there is a tendency of the uranium 235 molecule to leak through that barrier more than the uranium 238. So what do? You bring in a mixture of the molecules, 235 hexafluoride and uranium 238 hexafluoride through, let it diffuse through a barrier, and you end up with an enriched amount going through the barrier. And you repeat the process in cells. That's 2 or 3 of those cells in the actual plant, 1 and 2 here in a very, very elaborate process. Now, those devices in what's called the gas diffuser used initially simply galvanized steel, and then they discovered that the process is extremely corrosive, so they electroplated the steel with nickel. And then some bright gentlemen came out from chemistry or material science and said, okay, well, why not have an alloy of the iron and the nickel? In that case, the nickel forms on the surface a very thin layer of an oxide, and it resists the corrosion from the fluorine. Fluorine, remember, hydrofluoric acid is extremely corrosive. It's used for etching nice figures on glass, for instance. And this is what we benefit from today as what we call stainless steel. Stainless steel has an alloying element, nickel and chromium, and they form an oxide on the surface that doesn't let the rest of the steel corrode. So this is a spin-off of that kind of a technology. So many technologies start for military applications and they turn into civilian applications. The separation of that uranium 235 hexafluoride from uranium 238 hexafluoride in a single cell is very, very, very minute. It's very small. So in that case, we need to repeat the process on an industrial basis. The separation factor is interestingly the same as the square root of the mass of 238 to the mass of 235, same as in the case of the Kalitron process, but you have to use a cascading process or an industrial process. So let's start from the bottom and see how it goes. You pump, use lots of electricity. The plant that was used in that case used as much electricity as the city of New York. And that's why the Tennessee Valley Authority still exists today as a government-run utility in Tennessee to provide power to the Department of Energy complex electricity, but it also provides electricity to Alcoa. Alcoa is the aluminum company of America based at Knoxville, Tennessee, very close to the Oak Ridge, Tennessee National Lab, and that electricity is used in the production of aluminum. Now, in that time here, the electricity was used to drive those pumps that pump the uranium hexafluoride in one stage. We ended up with an enriched type stream, and you have a depleted stream that you take back. Now, the enriched stream goes to the next stage, to the third stage, follow the arrow to the fourth stage, fifth stage, and so on. And after 1,000 stages of processes, you can end up with that enriched uranium, say 95% or 98% enriched uranium. Each stage takes the tailings or whatever has not gone in the positive direction back Look here, it's added back to the previous stage. The tailings is taken back to the previous stage. So it's a process that's called the cascading process, a very large industrial process, and the separation factor is maybe only 1004. So that's why you need a very large number of stages in that gaseous diffusion process in very large cells. This is a hall containing some of those cells, and that was done in a plant that was 1 mile in length. They called it the 1 mile long plant. The French are still using that process for their nuclear reactors. And the interesting thing, they provide the power to those diffusion plants shown here by 1, 2, 3, 4 PWR, pressurized water reactor. You could see 1, 2, 3, 4 here. This is a turbine plant. This is a cooling tower that they were using. And this is 1, 2, 3, 4 plants for the enrichment. Obviously, they have different levels of enrichment, a large number here, a smaller number, and the smaller number may be for the very high enrichment that they would use for naval propulsion and maybe earlier for weapons. In the United States, we had several of those plants. It wasn't just one of them. This is what was named the K-25 gaseous diffusion plant. That was at Oak Ridge, Tennessee. It's no longer operational. The French one is still operational. Another one was at Portsmouth, Ohio, gaseous diffusion plant, also no longer operational. And just there is no need for all that uranium-235 after the Cold War. And there was one at Paducah, Kentucky. That was the only operating plant as of 2008. All those plants use, as you have noticed, tremendous amounts of electricity. So they were, and they are basically being replaced gradually by another process, the centrifugation process. So we covered so far how many methods for uranium enrichment. We have the thermal diffusion, we have electromagnetic separation of the Kalitrons process, we have the gaseous diffusion, but comes centrifugation, which is a combination of a mechanical process of a centrifuge and thermal diffusion to separate the uranium. And it has become almost a standard because it uses much less electricity than the gaseous diffusion or the electromagnetic separation. The centrifugation process basically uses a centrifuge that you yourself may have used in any chemistry lab. So if you rotate a liquid containing solids at a high rotational speed, the solids simply move to the outside and you can separate them from the rest of the liquid. So that's a very simple process. It would have a separation factor in the same way as gaseous diffusion and as the electromagnetic separation. The equations governing the process of separating work power is there if you want to design a centrifuge. And the important thing is that it is extremely high tech. The centrifuge rotor rotates at its periphery almost at the speed of sound. So you need something that's very light so that you don't break the whole system apart by the centrifugal force. And you have something that has a very, very, very high strength. So many different materials have been used in those centrifuges. For instance, high strength aluminum has been used, alloy. It has a low density, so it's light. And the peripheral speed of the outer rotor of the centrifuge can reach 425 meters per second. Titanium has been used. Titanium has definitely a higher tensile strength than aluminum. In newtons per millimeter squared, aluminum is 520, titanium is 920, but there is high strength steel that can reach even better than titanium. Maraging steel is super hard alloy, can reach 2250. Glass fiber composites have been used, 700, comparable to high strength aluminum, but the real success has been with carbon fiber composite. That one has a tensile strength of 2000 newtons per meter squared. The maximum peripheral speed of the centrifuge reaches more than 800 meters per second. We don't know exactly. And in addition, As another figure of merit, than other than the tensile strength, we need also a material that has a very low density. So again, here you find aluminum is good, but carbon fiber composite is even better. So in that case, if we take as a figure of merit the tensile strength uh, divided into the density, the carbon fiber composite just beat out all the other high strength materials shown here. So that is the trend in using, or the high tech in using centrifuges is using high carbon fiber. Let me quickly show you that how the centrifuge rotation concentrates near the periphery, a higher concentration. This is the radius of the centrifuge, the uranium-238 hexafluoride relative to the uranium-235 hexafluoride. So there is a higher concentration near the periphery of the heavy isotope, and a higher concentration of the lighter isotope near the center of the centrifuge. So as you rotate the centrifuge, you get a concentration near the center of uranium-235. So what do? You scoop it out and send it to another centrifuge, and you create a cascading process in a bank of centrifuges. So configuration of the centrifuge is shown here. You basically have coils of a linear induction motor. As you send the electricity, the electrical current in those coils, it rotates the rotor inside the centrifuge. You create a vacuum around it. And then we said that the lighter isotope concentrates near the center. So that's a product. You scoop it out and send it to another centrifuge. The aspect of the technology also is that because of the very, very high speed of rotation, initially they used needle bearings, but this wear very quickly and the centrifuge can vibrate. So magnetic bearings now are being used both for the electric motor as well as the bearing at the bottom here. So that's being carried by a magnetic field. So it's this magnetic bearings are used in the maglev trains, if you know, magnetic levitation. So you don't have friction between the wheels of the train and the track. And it's also used in jet airplanes. They get replaced after every flight, but they can help achieve very, very high rotational speed. So the high technology in centrifuges is using today the for strength and being light and overcoming the centrifugal force, carbon fibers, but also magnetic bearings are another part of the very advanced technology of centrifuges. This is an actual picture of, it is not one centrifuge or 10 or 20 or hundreds. They are, there are practically thousands of them in a given plant. This is the Urenco plant, which is in the UK and the Netherlands, located in the UK, actually located in the Netherlands. And this is a similar centrifugation plant used in the United States. You could see that it's thousands of centrifuges. And if you read the news, that is some sort of political kind of discourse with Iran. They're only allowed a certain number of centrifuges because depending on how many stages you are enriching the fuel, you can reach higher and higher enrichment. Nuclear power plants, a light water reactor, need only 3 to 5% enrichment to start operating. According to the Non-Proliferation Treaty, a country is allowed to reach the 20% enrichment in its fuel. But if you need to build the naval propulsion reactors, you need to reach the 90%. Brazil is doing it, even though it's but nobody raises hell about it because they have basically just forsaken the manufacture of nuclear weapons. But there is a suspicion that Iran may be pursuing those weapons. So it is the topic of great problems in terms of politics. This is a picture of those centrifuges. You could see that they can be extremely long here. This is the American design. Look at that gentleman here next to it. It's a nightmare in the plumbing, especially at the bottom of the centrifuge. The centrifuge operates there, but moving the gas from one centrifuge to another is a nightmare, as you could see here. And they're positioned in large, very large plants. This is a set 3 centrifuges, generation 3 centrifuge in the United States. Again, the gaseous diffusion and the magnetic separation are all have been forsaken, and the centrifuge process is the one adopted today. Depending on the number of centrifuges, if you feed the feed of natural uranium hexafluoride here, you end up with tailings on this side, and you end up with the product on this side. Now, you can use 100 centrifuges and get 3 to 5% maybe enrichment. But if you start increasing the number of centrifuges into the thousands, you can enrich to much higher and higher levels. So the process basically is again a cascading industrial process, and it's very, very, very high tech in that case. There is research going on the building better centrifuges using, say, a plasma. So you could see here that's a lab centrifuge using a plasma in the center. And then you basically create some kind of separator between the heavy isotope on the outside and the lighter isotope at the center of the centrifuge in general. Okay, not to be outdone by, say, let's say the list back again: thermal diffusion, electromagnetic separation, gaseous diffusion, centrifugation. South Africa and Germany developed a process that they call the aerodynamic nozzle and vortex processes. There isn't much in the literature about it, but in essence, what they do is that they create a flow of, say, the uranium hexafluoride, and then they send it through a curved kind of a surface. So if you send it through a curved surface, you create that separation process with the heavy isotopes being near the outside and the lighter isotope being near the inside. So they bring in a wedge and separate the two flows and repeat them over and over. While the process has is kept basically as some kind of a secret, so it is not very well known. There is another methodology that has been developed using lasers. Two methods, in fact, using laser, and we designate them as laser isotope separation. The idea here is that the different molecules of uranium-238 or uranium-235 get different excitation levels by if you excite them with a laser. So you find that for uranium-235 and uranium-238, this is 235, the excitation level, and this is 238, the excitation level. So you use the typical shift is only 0.1 angstrom. This is A with a little circle on top of it, a hat there. This is the angstrom unit, which is 10 to the -8 centimeter. It's used for measuring wavelengths in general. So these would be the typical excitation cross sections for the two molecules, and this can be used to advantage in separating them by two processes that were developed. One is called the molecular silex process. Very little is known about it too, because it was developed at I think the Lawrence Livermore lab, or is it the Los Alamos lab? I think it's the Lawrence Livermore lab, and an Australian company called Silex have adopted it, as well as the United States Enrichment Corporation. Basically, it also is evaluating the process. It's a very sophisticated process. So you start with a uranium hexafluoride 235. So think about the molecule like this, like one molecule, the center is uranium 235, and you have 1, 2, 3, 4, 5, 6 attached atoms of fluorine, UF6. Now what you do is that if you irradiate it with an infrared laser, you excite some of those molecules on the periphery, which is a fluorine molecule. So if you eject one of those atoms of the uranium hexafluoride, by following the infrared laser by an ultraviolet laser, you can get rid of one of those fluorine atoms, and the molecule becomes uranium that's pentafluoride. And the uranium pentafluoride, interesting enough, is not a gas anymore. That is a solid. So by having a flow of a gas, uranium hexafluoride, irradiating it with an infrared laser, then following it by an ultra that excites a molecule, then an ultraviolet laser de-excites it. You turn your gas into a, for the uranium-235, into a powder. And then, of course, all you do now is use a filter and filter the powder from a gas. Well, it seems easy, but it is a very elaborate process. So you need a carrier gas. The carrier gas is hydrogen. And if you use hydrogen in an industrial process, it's very highly reactive. So you have to be careful not to get an explosion. So you end up with basically tails, as you could see here, the infrared laser exciting the molecule, the ultraviolet laser de-excites it with the carrier gas as hydrogen. You end up with tailings as uranium hexafluoride 238, and the product would be uranium hexafluoride 235 by just using, moving the gas through a filter. And you end up, of course, with tailings of some 236 plus 235. That is one laser process, and we don't know much about it, except that we know about the lasers. This is a krypton fluoride halogen. That would be an ultraviolet laser. Another process using isotopic separation is called the atomic vapor laser isotope separation, AVLIS. In that case, you use atoms, use basically molten uranium in a crucible. You irradiate it with an electron beam, you evaporate it. Now you have an evaporation of the evaporated ions of uranium-235 mixed with uranium-238 and 235. You irradiate it with a laser here, and you have a plate on the top. When you irradiate it with a laser, you excite the molecules so they get a higher rotational radius, so they hit those plates, and these become the collectors or the product collector. That is where you get enriched uranium-235, and uranium-238 is simply collected on the top plate, or they call it the tails collector on the top. A plant actually has been built in the United States along these lines at the Lawrence Livermore National Laboratory, and they used it also for separating the plutonium-239 from plutonium-240. Plutonium-239 is a material used for nuclear devices, so that was a military program compared with plutonium-240, which is unsuitable for making weapons in general. Another method is the plasma ion cyclotron frequency separation process. This also is not very well known, but it is used by the United States Navy. As I suggested, naval propulsion needs very high enrichments in the uranium-235 isotope. However, over time, the uranium-235 isotope absorbs a neutron and becomes uranium-236. Now, the enrichment of naval reactor fuel can be 65% or 90% enrichment in uranium-235. So you'll find that with over time, the uranium-236 can reach 35%. So what do they do there? They take the fuel, evaporate it, and use something similar to the electromagnetic separation. In that case, you will get a plasma source, you evaporate the ions, and then you have plates here. And it is very obvious that because now you have a coil here where you circulate a current, so you create a magnetic field. So it's similar to a certain degree to the Kalitron process. And at certain cyclotron frequencies, you find that uranium-235 can take a very large radius rotating around the magnetic field line. As it has a larger radius, it can hit those plates that come into the flow from the plasma ion source and deposit itself, the 235 on those plates. The 238 are not excited as much, as I can go in between the plates and you get the tailings at the end of the process right there. So this is apparently used for the re-enrichment of the fuel for naval propulsion. And for instance, if you have no plasma separation, you can have a mixture of uranium-234, 235, and reaching 35% uranium-236. You put that fuel through that process of the plasma cyclotron separation, you can increase the enrichment of 235 to 69% and decrease the proportion of 236 from 35% to 26%. I wrote here 3 lines about another process called the chemical process. It has been basically some kind of talked about by the French, but no much detail in the technical literature appears about it, so we really don't know. It has, and it's a chemical process. Now, most of the processes we are talking about here are physical processes. They depend on the different properties of different molecules of the heavy isotope 238 and the light isotope 235. This one is a chemical process that depends on the valency in oxidation and reduction, and basically they use organic phases, so it's a chemical process. We don't know much about it. There is a process that came in out I was asked to review it, but it couples the laser process with the electromagnetic separation, but it has been suggested for the light isotopes, like separating lithium-6 from lithium-7, maybe for future fusion reactors application. So you could see here the lines separating depending on the excitation in a laser, as well as this is the simulated ion trajectories in separating lithium-6 from lithium-7. So the process is under really still, well, it is a new technology. The name for it is now isotopic tailoring. You tailor the materials that you are using into different isotopes for different uses. That's re-enrichment of recycled uranium. And in the United States, the enrichment process was basically a government activity, but it was being done by the United States Enrichment Corporation, but that corporation has been basically made public. So that company, USEC, has a license for 30 years, and it has only a mandate to enrich uranium no more than 10% in uranium-235. They are using the centrifuge machines and using those American designs of the centrifuges. They're using, look how many, 11,500 machines deployed in 2012. The American centrifuge plant basically is expected to use 95% less electricity than a comparable gaseous diffusion plant. So all the gaseous diffusion plants are being retired in favor of the centrifuge process worldwide. Some countries are still pursuing the research on the laser diffusion, but centrifugation seems to be the main line right today. I'll give you some problem for just to understand the mathematics here about how an executive and an electric utility will order for a power plant that has a certain amount of power for a given enrichment. Now, if you use a CANDU reactor, it's very easy. You don't need to enrich the fuel. So it's a matter of calculating the burn-up ratio and then the conversion ratio dividing into the natural enrichment of uranium. And that's what you have to order for a heavy water reactor from the mine. However, if you are using a light water reactor, so we have really 2 problems here to think about. If you have a pressurized water reactor, you have to put the process through the enrichment process, and you decide how much enrichment you need for your fuel, 3 to 5%. And then you end up with the mass of the product, and then you convert that into the mass of the uranium that you have to contract to mine to produce the fuel for you. So that really covers our chapter here. Let me go back. Our section on what are the different approaches that we use for nuclear power plants. As you could, if you remember, these processes, some are the existing technology, but we have as many, even more, on the drawing board. So we covered all those chapters right here. I would like, since this is very quantitative today, it's a little hard, I would like to get into a fun chapter. And that fun chapter has to do with the Oklo phenomenon. Let me see, where is that Oklo phenomenon? The Oklo phenomenon, the Oklo name is a site in the Gabon Republic in Africa. And humans basically thought for a long time that they have invented fission that we have been talking about right here. But in fact, at some time that was not discovered, it was not the case. And nature has beaten humans in terms of the energy production. So let me find the natural reactors chapters. Here it is in the part 1, natural nuclear reactors, the Oklo phenomenon. This is a fun chapter, and it shows us that we have to be really humble and very modest in the treatment of science in general. In 1972, remember, nuclear energy fission process and so on was discovered in 1940s. So 30 years later, basically we discovered that nature has beaten us humans into creating a nuclear natural reactor. And that happened in Western Equatorial Africa, in the Gabon Republic. And it happened at a mine called the Oklo mine and another mine called Okilobando mines. They were run by the French, and Bango, baby, mile 35 kilometers away. And the whole idea was studied by a French physicist, Francis Perrin. And what he noticed is that when the uranium ore mined by the French in that case, because these were French colonies, that the enrichment in uranium-235 of the ore that is coming to the plant that separated the uranium from the mine was 0.717% rather than 0.720%. So look here, this is a very interesting scientific endeavors. He simply didn't accept that smaller number here, even though it's a very, very small difference. And so they investigated the idea, but it has also a strategic implication. Where did that uranium-235 go? Did somebody steal it? It has non-proliferation issues in that case. In the end, they discovered that natural reactors have become critical in nature. And about 1.8 billion years ago, let's say 2 billion years ago, eon is a name for a billion years. And one of the reactors that were discovered, now initially they only discovered one site, so they thought, oh, it was one reactor. And a Russian scientist suggested that was maybe the site of an antimatter meteorite that hit the area. Like if you watch TV right now, they have some kind of a program on some ranch out west that they say, oh, it exhibits abnormal phenomena. Well, I can think about an antimatter meteorite or just plain meteorite that hit the earth there. It produced 15,000 megawatt thermal years of energy, and it consumed 6 metric tons. Now remember, metric tons, T-O-N-N-E-S, is not the same as T-O-N-S. 1 T-O-N-S ton is 2,240 pounds. This is the American or British units. Metric ton is 1,000 kilograms. And it operated over 100,000 years, on and off, depending on whether there is moderation by water in the area of the mines. It consumed 6 metric tons of uranium, and it operated at a very low power, only 100 kilowatt thermal, whenever water was interacting and moderating the neutrons in a uranium mine. So from 1942 to 1972, humans were some kind of arrogant. They thought that, oh, they discovered a new process that doesn't happen in nature. But no, nature beat them to it. This is an ore sample from that Oklo mine. That would be how the uranium at that mine would look like. Notice that it is incorporated in what looks like clay. We'll see why that happened. This is, if you visit sometime Austria and go to the Vienna Natural History Museum, go to the Oklo exhibit, and you can see that with your own eyes. This is a picture really of the mine in the Gabon Republic. You notice here the slope of the land, and you notice the yellowish kind of hue of the U3O8, which we call the yellow cake. And notice again the very deep slope here. That is where the uranium is being mined on the side, on the slopes. And at the bottom here, you could see that lots of water is accumulating. They call this zone 2 of the mine. Where this, we said that these natural reactors happened about 100 million years ago from present. And at that time, the continents were all connected together. As this is what geologists tell us, into one single big continent called the Pangaea, or the Pangaean supercontinent. There was some ice near the North Pole and some ice near Antarctica. But over time, those continents now are separating from each other. You know, the Mediterranean separates Europe from Africa, and South America, the South American continent is being separated from Africa. You could see that the South American continent and Africa were joined at some point about 100 million years from present. And it was called the Pangaean supercontinent. So that area was a maritime area, like part of water from what became eventually now the Atlantic Ocean, and it was more like marshes. I'll come back to that point later on at the end of the lecture. So the Gabon Republic was at that point here in between the South America and the African continent. The two continents, of course, have separated, but it's the site of the Oklo was right here at that point, right here. That's now what we call the Gabon Republic in in Western Africa. How did they discover it? This is some very interesting process of scientific investigation on how you can discover new realities by being suspicious of the data that you have and analyzing it and reaching deeper understanding. Our state of knowledge about the isotopes of uranium is that we have three isotopes. 235 is 0.72% in atomic percentage. A/O means atomic percentage. If you write W/O, that's weight percentage. If you write V/O, that would be volume percentage. In any way, that's 0.72%, or one atom in every 140 atoms of uranium is uranium-235. So most of the uranium we have today is the uranium-238. 99% of uranium is uranium-238. As uranium-238 decays, it produces uranium-234. So in fact, we have a combination of the three. Notice the higher abundance of 238 is associated with a very long half-life, 4.5 billion years half-life. 235 has a shorter half-life, 7.7 billion years half-life, and the 234 has an even shorter half-life, 2.4, 10 to the fifth power. So this is a situation today. We have a mixture of the three isotopes, yet it's a 235 that can readily fission in our existing reactors to produce power. So at the plant that received the uranium from the Gabon mine, they analyzed the concentration of uranium-235. And this is data that you can find in microfishes if you go to our physics library. That's where one student who published a paper with myself figured that out. So it's in French. And what they did is that basically they showed here percent use 5. That's a percentage of uranium-235 in the uranium ore as they kept mining it over time and around 1972. So you could see here the scale is a decreasing scale. This is a 0.72% enrichment of uranium-235. And you could see that it started, let me increase that in size. It decreased a little bit to 0.7, and then it increased a little bit again, and then it decreased back again to 0.7, 0.69 maybe. So they started suspecting something there, that something is wrong. So what do? They went to parts of the ore that had a higher concentration in uranium-238. This is the teneur uranium in 1,000, 20 in 1,000 here, not in 100. This would be percent 1 in 100. And even though they went to a higher concentration in the ore, instead of getting a higher concentration, the scale goes down here of uranium-235. No, it went even less. And the more ore concentration they get, the worse the concentration of uranium-235. So that was a puzzle for them at the time. And the concentration in uranium-235 reached 0.62%. So something happened to that uranium-235 that made it disappear from the ore that they were, and that's another way of displaying it, that the higher they mined ore that contains more uranium, the lower the concentration, 0.72 of uranium-235 that they kept going. So that was worth investigating. And notice that this is a publication in French. So in Europe, what we use in the United States is a period, 0.72%. Enrichment in uranium-235, basically they use a comma in that case, O, comma 0.72. Notice 235 decreasing as they increase the proportion of a more richer ore. So they thought that if they get a more richer ore, they'll get more uranium. Came the geologists to study the process, and they suggested that from the pictures that we have seen earlier, that the geological events have happened in that area. First, that basically the South American continent has separated, in fact, from Africa, from the Pangaean continent, the Atlantic Ocean formed. But at the time where the geology of the process happened in Stade 1, this is stage number 1, Stade 2, second stage, Stade 3, which is stage number 3, that the area was primarily a rock base, sock here, covered with water in a marshy area. So it was marshes, there was water available there. And then the tectonic movements of the plates of the earth made one side of the base rock rise in the second stage. And in that case, it dried out the water from the marshes area. But initially, it was a marsh area where uranium as a heavy element deposited itself in the flow of the water. And it was mixed with water and algae. Algae actually concentrate some metals in general. Sometime in the future, we might extract metals, even gold or uranium from algae that concentrated in the oceans. So at that time, it was this mixture of a wet environment water that came in and went out, meaning that it dried for a while and then started getting wetted back again with the movements of the tides and the movements of the tectonic plates. At some point, the slope has been so steep that basically the whole thing has dried out in our present time. And that's what we see in the very early pictures here. You could see how the slope has changed very, very dramatically, but there is still water there at flowing at the bottom of the mine. Uh, so let's go. Okay, so this is it here. Uh, so at some point, you could see that according to the geologists, the uranium was being flooded and then unflooded, drying and getting wet. And when the water is available, we know that water acts as a moderator. It slows down the energy of the neutrons to thermal energies. And in that case, they can cause the fission in uranium-235. Okay, wonderful. What is the nature of the ore? This is a micrograph here. It'll show you that the uranium is really mixed with kaolinite. Kaolinite is an ore of aluminum, so it's more like a mud, if you want to call it, or clay. Clay is a more, and that clay became rich in water, and with convective motion. This is one of the sample, like the one that I've shown you in the Vienna Museum, that's magnified 100 times. So it may have looked at the time when those reactors happened in nature, very similar to what you find right now at the Yellowstone National Park. If you go there, you'll find, because it's a caldera or the cauldron of a volcano, you find there what's called mud holes. So you find the mud basically boiling out. So it was a form of that mud mixed with the uranium, the water acting as a moderator and the uranium acting as a fuel. And so they went into more detail, analyzing the isotopic content, and isotopic sampling in that case can give us an insight into what happened to those ores. First, they looked at uranium in nature. We know that uranium in nature, A/O means atomic percent, is 0.72%. But uranium in nature sometimes gets fissioned by cosmic radiation. So you find that we generate isotopes, particularly of neodymium. And look at neodymium, it has so many isotopes. Neodymium 142, 143, 144, 145, 146, 148, and 150. And there is also in natural abundance different ratios of the isotopes. That's europium 151 to europium 153. In nature, that is the ratio. Cerium 140 to cerium 142. Cerium is one of the rare earth elements, and samarium 149 to samarium 47. These are some kind of constant ratios that happen in natural abundances in the different elements isotopes. Now, if you fission uranium-235, you find that the composition of the isotopes, not like what happened in nature, is different. For instance, you do not produce neodymium-142 when you fission uranium-235. So it's a smaller number here. And you find that the ratios here of europium-151 to 153 is different, 2.58 instead of 0.9. Same for cerium-140. 8 times the ratio is a ratio of 8, but from fission it's only 1. Now, when they took the Oklo sample, one of the samples contained only 0.44% uranium-235. But look at this, the sample that they call sample M. You find that it didn't have the natural abundance of 27% neodymium-142. It had an abundance of 1.38. So it's very close to what you would get from fission with a little contribution from natural abundance. So what do? You adjust the sample of the isotopes for the natural abundance. And if you adjust for the natural abundance, then you get, then in the Oklo sample, it is 0. So definitely fission has happened there, 22.6%. This is very close to what happened in fission. So you get, you reproduce basically the isotopic content of the fission numbers in that case. You can get also some insight from the ratio of the europium, cerium, and samarium isotope. Definitely, it was fission that happened in those Oklo samples that reduced, in that case, the proportion of uranium-235. As I suggested, initially they had only one zone where they discovered those reactions occurring, and came a Russian scientist and suggested it may have, the uranium-235 may have decreased by a meteorite made out of antimatter hitting the Earth. That theory has been discounted because as they investigated the process later, they found not just one zone of the reaction or a natural reactor, but 1, 2, 3, 4, 5, 6, and eventually they found 15 zones in the 3 mines that they were mining, the French were mining. That's not pie in the sky. This is one of the reaction zones shown here. It is being kept as basically a word type of natural history phenomenon. Look at the large size of that reactor on the slope with the gentleman here, the geologist running, and it's another picture of it with, it gives you an idea about the size. And I found a third picture here with a gentleman there, geologist, pointing at what the zone, the outcropping of the natural reactors at the Oklo phenomenon. So about 1.7 billion years ago, nature beat humans to generating fission. The interesting thing here is that, as you remember in the table, that uranium-235 has a half-life of 0.7 billion years. So from 0.7 billion years ago, our 0.72% definitely was much larger before. It was in the range of 3 to 5%. So that was a situation that humans discovered when they built light water reactors with an enrichment of uranium-235 today of 3 to 5%. And we can prove this here with some with some simple equations that 2 billion years ago, the enrichment of uranium-235 was in the range of what we have now in our light water reactors. So nature discovered light water reactors before humans discovered them. And the process, of course, is a process of breeding of a neutron in uranium-238. We covered that last time. And over those billions of years, you notice that your plutonium also has decreased in, it's also decaying with a much shorter half-life, turning into uranium-235. So that was a very complex process in general. Now, what are the factors that led to the generation of those natural reactors? It has to do with the fissile to fissionable ratio, the amount of uranium-235 relative to uranium-238. And the higher the enrichment in uranium-235, you find that you get different criticality conditions. So let us, if we neglect that 234, which is a very small in number, we can do an analysis of the enrichment as a function of time of the number of atoms of uranium-235 relative to the number of atoms of 235 plus 238, which is that 0.72% that we have today, or the 100 in 140. Now, each one of those isotopes, 235 and 238, decays according to its own decay, the radioactive decay law. So let's plug it in here, except that each one of them has a different half-life. So now we can get the enrichment that we have today, 0.72%, as a function of the decay constant or the half-life of 235 and 235 and 238. Okay, now the question that we ask ourselves, all right, what was the enrichment at the time of the Oklo phenomenon? So what we want to do is calculate the tau. So we have to carry on what's called an inverse type of an analysis. Given the enrichment today, what is the tau time where that happens? So we manipulate the equation, we get 1 over the current enrichment, Then we bring the 1 with 1 plus 1 over the current enrichment. And then we get the ratio of the initial number of 238 nuclei to 235 nuclei. Then we turn that into an enrichment in the past, 238 divided into 235 plus 238. And then in that case, we try to take the invert of the denominator, and then we take the natural logarithm of both sides. When we do this, you'll find that we can get the value of tau at different times in geological time. So today, this is the enrichment today, that's geological time in billion years of year before present, that's BP. But 2.1 billion years ago, that's the time of the when the phenomena occurs. You notice that substituting in the equation, we find that the enrichment was 4%. So we can prove it just analytically here by plugging in the numbers. So over time, that ratio has decreased. The ratio has steadily decreased of 235 to 238, and 2.1 billion years ago, it was at the same level as we are using in existing nuclear power plants. So the first factor is definitely the amount of 235 relative to 235 plus 238. Another factor in the reactions that happened, and we'll use this to learn more about how to achieve criticality in existing nuclear power plants, is the water to uranium ratio, or the moderator to fuel ratio. And as we know that when the area was flooded, the reaction went on. So we can quantify this by imitating or getting insight from what happened in bacterial populations when they multiply. And we use what we call the multiplication factor. We name it K, except that instead of bacteria, we talk about the number of neutrons in a given fission generation, not bacterial generation, relative to the number of neutrons in the previous fission generation. This multiplication factor depends on 4 factors, and this is what we call the 4-factor formula, and we are going to use it after the test to learn about the criticality on the theory of nuclear reactors. So we start here by defining the multiplication factor as what we call the regeneration factor. That's the number of neutrons born in fission relative to the ones absorbed in the fuel. Some fissions occur at fast energies. This is accounted for by the fast fission factor. Then we have what's called the resonance escape probability. That's the probability that the neutrons will escape being absorbed in the resonances of the uranium-238 nucleus. And then we have the fuel utilization factor, which is a proportion of neutrons absorbed in the fuel relative to the neutrons absorbed in all the other processes. And if we plot, let's take epsilon as a constant and eta as a constant. If we plot P, the resonance escape probability, against F, the fuel utilization factor, and put it in a table here, that's a fuel utilization factor. This is the resonance escape probability. Multiply them into each other. You find that when depending on that moderator to fuel ratio in our equation, you'll find that the product gives you here 0.55 for the infinite media multiplication factor, whereas you can reach a maximum when you multiply the fuel utilization factor at 0.89 multiplied by 0.84. You find that your infinite media multiplication factor can reach a maximum. We have taken the epsilon as unity in that case. So you could see that under certain conditions of fuel utilization and the moderator to fuel ratio, if you have more moderator to water, you can reach criticality. But here, the infinite media multiplication factor is less than 1, so the system is considered as subcritical and you cannot have a chain reaction. This is going to happen in the same way in existing power plants when we start the third part of the semester. Another factor in reaching criticality in the Oklo phenomenon was the critical size of the ore. Remember, it had the shape of a large sphere, And when you have a sphere, the surface to volume ratio, if you take 4 pi r squared divided, this is the surface area, this is the volume of a sphere, you find it's equal to 3 over r. So in that case, you find that the larger the radius of the sphere, the lower the surface to volume ratio. Hence, this has to do with the neutrons escaping from the surface of the sphere. So that infinite media multiplication factor can become an effective multiplication factor if we have a specific volume. So we define what we are going to call the fast probability of leakage of the neutrons and the thermal probability of leakage from the neutrons. We'll come back to this later, but in essence, if you have a small sphere, you have a large proportion of the neutrons escaping from the surface. If you make it bigger, the proportion, you have more fissions, but the proportion of neutrons escaping from the surface is decreased. So the people at the Chicago pile number 1 were increasing that volume. One interesting aspect, of course, effect of the neutron poisons. When fission occurs, some materials are produced that absorbs the neutrons and can slow down the chain reaction. And an interesting aspect in terms of the disposal of fission products or nuclear waste is that all the fission products in the Oklo phenomenon remained at the same spot. For those of you who like to become maybe Indiana Jones and explore, it turns out that in Canada, in Colorado, and Joam that's South Africa, you find that uranium-238 to 35 ratio is not the 142. So there is a way that maybe those natural reactors may have happened, oh well, in Colorado, in Canada, in South Africa, not just at the Oklo phenomenon. So according to James Lovelock, an environmentalist person, he suggests bacteria could not have debated the costs and benefit of nuclear power. The fact that the reactor ran so long that there were not more than one of them suggests that replenishment must have occurred and that the radiation nuclear waste from the reactor was not a deterrent to that ancient bacterial ecosystem. So nature basically recycles itself, and we are here just watchful of nature. We try just to imitate what nature is doing, and we have to be very, very modest in terms of our knowledge of the universe around us. Everything covered today, including the assignments, will be covered in our tests on Friday. I'll make it a little easier. Some people complained the first test was too difficult. We'll have 3 questions instead of 5, and it should take you half an hour to solve the test, but please work on the problems that are in the assignments.